It is OBS.
Yep.
Yep, in Linux. Yep.
Yeah.
Most stuff that I need to do, they all work in Linux except for League of Legends. But it's okay. I'm a wimp. I only play bot games, so it's not a big deal. Alrighty. So where's my browser? Over here. Great. Okay. All right, so the mic is on, the recorder is on, so I can get started with the class. So I'm hoping that most of you know where to find the class recording on YouTube. The channel name is SOMEPROFs, SOMEPROFS. So all the lectures, if I remember to turn it on and remember to change them to the record using the mic, the recording will be there. So any questions about that part? No questions? Yep, go ahead.
Are you going to use a document camera this semester for certain things?
Yeah, for when it is time to use a document camera, I will use a document camera, which takes a little bit of time to set up, but it's really great. Yesterday I was at Costco and they had the Samsung Galaxy Tab S3 or something like that that is pen-based. So I thought about getting it. It's almost $600. Then I go like, well, the document camera is already here. I pay like $40 for it, from eBay, and paper's basically free. So I go like, I kind of like the tactile feel of paper anyway. So I'm gonna use that approach. And we are using Canvas this semester, so most of you know that already because of the discussion of the syllabus. All right. And I only have one section of 440, so the only one has got to be it.
Are you teaching that many classes this semester? Are you teaching that many classes this semester?
Well, they separate the lab and the lecture into two different quote-unquote entities in Canvas, so it appears a lot more than what I actually teach. I'm teaching this class in two sections of CISP 310, and that's it. That's my teaching load. So not too bad. So all of the class material, okay, do you guys have any questions for me?
Sure.
Okay, so all of the teaching material are quote-unquote modules, and I use that term modules way before Canvas even was created, okay? So when I say my module with a number, it had nothing to do with the terminology in Canvas. So anyway, so there's this part here, that talks about taking a class from TAC. It is completely optional reading. You don't have to read it, but if you want to kind of look at your own personality type and look at my personality type and figure out, okay, so certain things will work well and certain things may not work so well. So that can help you kind of understand it and go like, okay, so that means I need to ask more questions in class, okay? Because TAC may go a little bit fast sometimes, and if I need to, do that, I'll just raise my hand and say, okay, I'm not quite getting that. Can you explain that again? Or just confirm your understanding. It's like, okay, TAC, if I understand this correctly, you were basically saying da 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 da. Okay, so all of those things are stuff that you can do in class to help make your experience in this class more successful. Truth about truth is just a general discussion. So the real content, I'm going to open this up too, and then this one. Okay, so the truth about truth is really just a general discussion of what type of definition, what type of truth are we dealing with here. We are not dealing with truth that can be discovered, that is reality. We are talking about truth in a definition way. Okay, so everything, all the rules that we talk about in this class are basically definitions. This is not a science, okay? Computer science or mathematics is not a science. We are not discovering how nature works. We are making up rules that are basically self-consistent, and then see how far we can push with those rules. Now, are they actually useful? Sometimes, most of the time. But sometimes we may not find a use of a result in mathematics until years and years and years later. Okay? So if you want to kind of find out stuff about this, you can check out people who study pure math. not applied math, but pure math, they come up with all kinds of artifacts of consistent logic and theory in mathematics that has no actual application. Physics doesn't need it. Okay, chemistry doesn't need it, and so on. It's only usually after decades, if not centuries, that people will say, okay, we are now starting to observe these particles or the interaction of those things and whatnot. And then they discover that centuries ago, somebody has already derived the mathematics to model that sort of thing. They go like, oh, great, I just need to reuse something that has been already derived, but hundreds or at least decades ahead of the time. Okay, but computer science is a lot more applied, so we typically don't have stuff like that. Although many of you, when you go to a 4-year university, you might get a sense of that, because Alan Turing, who is considered the father of computer science, the way he looks at computers is very different from the way we look at computers. We look at computers as, okay, it's got a processor, has got RAM, has got ROM, has got hard drives, right? It executes instructions one step at a time, at least on a per core basis. You might have 8 cores, 12 cores, and whatnot, but each core is still a pretty simple thing, okay? Taking the instruction, taking the opcode, go to the memory, get something to process, store it back in the memory, talk to the hard drive, store something, grab something, and so on. That's not how Turing looks at computers, okay? If you want to look it up, it's called finite state automata or finite state machines. That's how he looks at computers, which is very different from how we look at computers. And the theories that he came up using that particular way of looking at computers is still valid today. Okay, every single computer, physical computer that we have today still has to play by those rules. There are problems that these computers simply cannot solve. Okay, that's the one of the theorems that Turing came up with is there are problems that a computer cannot solve. A Turing machine, which is the most complicated, most capable machine that he can come up with, cannot solve certain problems. Those are the things that we are not going to talk about in this class, okay, because this class is equivalent to a lower division class at a 4-year university, and what I just talked about are things in the upper division in a 4-year university. So the first real content of this class starts with Boolean operators. And because you're in this class, I'm assuming that you have taken, or you're at least co-taking cisp440. And also there's a math requirement. What was the math requirement for this class?
370, which is pre-calculus.
Pre-calculus, okay. So, pre-calculus definitely would have to use conjunction and disjunction and stuff like that. Maybe not explicitly, but implicitly. But we'll go over this stuff here just to make sure that we understand what Boolean operators are and which ones are useful in this class. Okay. An operator in general is an operation that requires at least one value, and the operation produces its own value. So it takes one input, at least one input, and it gives you at least one output, or usually gives you one single output. So a Boolean operator in C++ is something that you should be very, very familiar with. The and, ampersand, ampersand, the bar, vertical bar, and the exclamation point are the 3 logical operators that are defined in C and C++. Is that okay? All right. A Boolean operator, okay, in C and C++, any scalar value that is non-zero is considered true in the context of Boolean values, and anything that is 0 is considered false. And that includes, addresses. If you have an address or a pointer that has a null address, and you are using it in the context of a Boolean operator, it is representing 0. It's representing false. Okay? So C is really confusing because it allows you to use things that are not Boolean in the context where Boolean is expected. Java doesn't let you do that. Java requires Boolean values where a Boolean value is expected. All right, so we'll go over the operators that you already know, and then we'll move into some operators that you may not know at this point. So let's talk about conjunction first. Okay, so the table here is it's really kind of spelled out verbose. Basically, it spells out the 4 possible results of conjunction, And by the way, this symbol here, it looks like a little inverted T. That is the mathematical symbol for conjunction, which is the same thing as ampersand, ampersand in C and C++ programming, or just AND spelled out in most other programming languages. But in this class, because it is actually a quote-unquote math class, I'm going to use, sometimes I would use the mathematical symbols. Is that okay so far? So you might want to just kind of write down a little bit of a cheat sheet, so every time you see a symbol like that, you know, oh, that's just conjunction or AND. Okay, so this is no big surprise, when you have, x being 0, y being 0, the result of conjunction is 0. When you have x being 1, y being 0, 1 and 0 is a 0. 0 is false, 1 is true. And the only case you have a true coming out of a conjunction is when you have true and true, which is what this particular expression is expressing. Okay, so 1 and 1, or true and true, is true. Are there any questions about this table, how it captures the definition of conjunction? Nope. It's all good. It's all good? Okay, all right. So then we'll go ahead and look at the other way of representing this table. It's less verbose. It's the same stuff. It is both. They're both defining conjunction. So with this one, I'm using the down arrow here to say that these two values are y's, and then I'm using a horizontal arrow here to basically specify these two values are the values of x. So this one is corresponding to x and y. I'm using a diagonal arrow here. So this is 0 and 0. This one is 1 and 0. This one here is 0 and 1. And this one here is 1 and 1. So it's just a more concise way of looking at a truth table instead of spelling it out like this. Just notation. So in Boolean algebra, in the context of computer science or computer engineering and electrical engineering, we use different type of symbols to represent conjunction. This is what you should be familiar with already. Okay, even if you took cisp440, which is data structure, in Java, they still use the same symbol to represent conjunction. To mathematicians, this is how they represent x and y. Okay, the little TP symbol represents conjunction.
Looks like A. That's how I remember it. Looks like A.
The A without the horizontal line.
Right.
Yep, that's the other way to do it. I look at it as a little TP. But to computer engineers and electrical engineers, they overload. Okay, since you all understand what overloading is, because you should have taken object-oriented programming already, where they talk about overloading an operator. So in computer engineering and electrical engineering, they overload multiplication to mean conjunction. So if the context is talking about Boolean values, multiplication basically means conjunction. So a lot of times you will see x dot y to represent x and y in this case, and you can even simplify that to just xy. So xy in algebra, okay, usually means x times y, because we're too lazy to write the multiplication symbol, right? But because multiplication is overloaded in certain fields, including computer engineering, to mean conjunction, so xy means x and y in that particular context. Are we doing okay so far with these various notations of x and y? Okay. So the next one is disjunction, which is known as OR in English, but you have to be careful not to use exclusive or either or, because those are slightly different. So the truth table looks like this. When you have x or, a 0 or 0 is a 0, but anything that has at least one side being true would have a result of true. Okay, I hope that matches your understanding of OR in programming. So moving on to the notation, this is what you use in C and C++. X bar bar y is x logical or y. And in mathematics, it's a V symbol. Okay, x and V, y, it represents x or y. In engineering, or in computer engineering and electrical engineering, they overload the operator plus to mean conjunction.
You mean
So,
You mean conjunction or disjunction?
Conjunction. I mean disjunction, sorry. Disjunction, I misspoke. Good job. Yep.
Well, we see the engineering version a lot in this class, or just the X with the kind of like TP upside down?
When I use a regular text editor to illustrate examples, it's really hard to use the TP and also the V symbol. So I would switch to the engineering notation, which is really easy to type using a plain text editor.
Okay, that makes it a lot easier then.
Yeah, but when I have the actual means to do proofs, using LaTeX, which is the typesetting software that I use to type all my notes, then sometimes I would use the proper mathematical symbols.
Okay.
So you just have to kind of get used to both.
Yeah.
Yep.
What LaTeX editor do you like?
Sorry?
What LaTeX editor do you use?
I use VI.
Oh, okay.
So I don't have anything special for LaTeX. But VI is kind of cool because I use Vim to be specific. It's VI improved. So it's got syntax highlighting, and it understands to a certain point, LaTeX. So it would highlight, the begin and the end text correctly.
Okay.
So it's actually pretty useful. Okay, so the last one is negation. Okay, negation is simply not. Okay, that's the word not in English. It's the only unary operator that we're going to use, which means it only takes one value and it produces its own result. So with a one single value, this is representing what x is. This is representing what is not x. This is x. This is not x. In other words, not false is true. Not true is false. No surprises here, I'm hoping. Okay? If anyone is surprised by this type of thing, it's time to go back to CISP 300, not even 360. Yep. This is what you're familiar with, the exclamation point and then the X, this is logical not, okay? Because in C and C++, there are two versions to for each logic operation. There's the bitwise and there's the logical. Okay, so in this class, we're only concerned about the logical operation. We do not use bitwise operators. So don't worry about the tilde symbol in C and C++ because that's the that's the bitwise not operator. In mathematics, we use this kind of little cliff symbol to represent negation. In engineering, it is more conventional to use an overbar to indicate it is a negation. But overbar is pretty hard to type in a regular text editor. So sometimes people use a slash to also mean negation. So slash x can be the negation of x. So in this class, I think I'm going to settle on using exclamation point as negation. Okay, so because that's just a whole lot easier to type on the regular keyboard using a text editor. All right, so are there any questions about the three logical operators that you used quite a bit in C and C++ programming? Questions? How about the various representations? How the different ways that we write it or type it? Any questions about those notations? It's just memorization for the most part. Yep.
So for the negation, you said even though the exclamation mark is how it's represented in C++, we're going to stick to that form just because it's easier to type. Right. Okay.
Yeah, I'm still kind of divided whether to use a slash or an exclamation point, because exclamation point makes it easier for you guys to remember because there's no confusion. It is division.
Yeah.
Okay, so now we're going to go into the other operators. Okay, the first one is a interesting operator, especially for those who are currently taking CISP 310 or have taken CISP 310 from me. Because I can only say it from me because other professors may not introduce the NAND operator at all in that class. So the NAND operator is a negated, that's what the first N is representing, is negated AND. In other words, it is a negated conjunction. It takes the conjunction and then negates the result of the conjunction. So in a lot of mathematical or Boolean algebra text, they use an up arrow to represent NAND. Now, don't ask me why. I have absolutely no idea why they chose up arrow to represent NAND, but that's what they chose. So that means these two expressions are equivalent. They are exactly the same thing. Because x NAND y is really just a very concise way of saying the negation of the conjunction of x and y. Okay, so it's just a shorthand. Now, yeah, go ahead.
So when you mean negating the result, that's like saying that if the result was 1, it now becomes 0. If the AND would have spit out a true, it would become false?
Yes.
Okay.
So one way to illustrate the NAND operator, I'm going to use a mouse pad here to illustrate it. And it opens it in a different window.
Probably.
Yeah, probably. It's already here, actually. There we go. Okay. So what we want to do, or what I want to do, is to show you this definition when I'm working out an example. Okay, so if I want to illustrate any binary logical operator, I can use the form of a truth table. So I can have x, y, and then we can have x. I'm going to spell out NAND y because I cannot type the up arrow symbol easily using a text editor. And I'm going to space it out a little bit more. So when x is false, y is false, then you look at the result of x and y first. What is the result of 0 and 0, or false and false? It's false, right? But a NAND will take the result of the conjunction and then negate it, apply a not to it. So it will be true.
Not false.
Yeah, not false is true. And you can probably see that this will also have this, because if at least one side of a conjunction is a false, the whole thing is false. So the first 3 rows will give you exactly the same answer. The only row that will give you a false as the result of NAND is when x and y are both true. Then you have true and true being true, but then the negation or the not of that is false. So that's NAND, okay? Which is a very odd operator because we don't use it in daily life, okay? You don't go to some place and use NAND as a logical operator, okay? Because no one else is going to be able to understand it. And it doesn't seem to be very useful either. It's like, well, why would we want to even talk about the NAND operator? Well, it is kind of cool because you can use the NAND operator to emulate all of the other operators that you already know. So, well, the first one, this one here, deals with simple negation. Do you think that is true? Not x really is the same thing as x NAND x. And if you suspect that is true, how do you validate it? How do you show that these two expressions are in fact the same? A truth table, exactly. So you use a truth table and you say, okay, what happens when x is false? Okay, not false is true. And what about the other side? False, NAND, false. Well, we just created a table, right? False, NAND, false is true as well. That works. What if x is true? Not true is false. Okay, that's one. What about false, NAND, false? We look at that table, that will give you true. So once again, they give you the same answer. So if for all the possible combinations of values for the parameters, if they all give you the same result, then the expressions are really the same. So this means, in Boolean algebra, to prove that two expressions are really the same is pretty easy. Because you just spell it out. You spell out every single possible combination of the parameters, and if the expressions give you exactly the same answer for every single case, then you have just proven that the two expressions are exactly the same. Can't do that in general algebra, but in Boolean algebra, this is doable. So that's kind of cool. What about x and y? Now, it's really kind of cumbersome to look at it, but it is true. So x and y is really the same thing as x NAND y, the whole thing, NAND, another x NAND y, the whole thing. So once again, you can use a truth table to prove this. And I strongly recommend, if you have time, okay, after the class, when you have time, go ahead and pick one or two of these things and just do it by hand using a truth table. It should not take you a whole lot of time, but it will give you the confidence that you understand what these operators are representing and you understand how it works. Okay. And then the last one is X or Y. X or Y looks kind of the same as X and Y, but you can see that they're different. X or Y is X NAND X, which is the negation of X, NAND Y, which is the negation of Y. Well, this is because of the application of De Morgan's law, which we will talk about a whole lot later in this class. Any questions about how this kind of cool little operator called NAND can be used to emulate all of the other operators that you're already familiar with?
So
Yeah.
is one of the things that makes NAND special is that we only need NAND to represent the other operators. There's like no other operator that really has that power.
I suspect NOR can do the same thing too, which is the negated OR operator can do the same thing. But the NAND operator is kind of strange or cool in one way because it is very easy to implement using transistors. Yeah, go ahead.
Because like the definition of NAND is basically and not. So, like it's like if you break it down, then you can extract the and not out of it by
Sort of. When I think you got the right idea of why it is more quote unquote expressive than the other operators. But the significance of the NAND operator, if you want to look it up, you can just look up NAND circuit transistors, and it will give you like a gazillion circuits to do that. It is one of the simplest operator to design using transistors, and that's why it is significant. Because when you're looking at the implementation of computers, the OR operator takes more transistors. If you want to implement a direct OR gate, it would take more transistors. If you look at the regular AND gate, it would take more transistors. But the NAND gate turns out to be pretty easy to implement in transistors. So that's the significance of the NAND operator. All right, so the next one is implies as an operator. So implication as an operator, in this class I used the double bar right arrow to represent implication. So let's look at the definition first. This is kind of the definition of implication. In other words, X implies Y is really saying the same thing as not X or Y. Okay, which may not map to what you typically use, implies, the word imply on a daily basis. But in mathematics, implication is really defined like this. X implies Y is the same thing as not X or Y. Which basically means if you want to figure out the truth table, you can just work out what is not X or Y. So this is already worked out. Whenever X is a 0, whenever X is false, you can see that this is taking the disjunction and one side is not X. So that means if X is false, not X is true. But if at least one side of the disjunction is true, the whole thing is true. So that's why you see that this is going to be a 1, this is going to be a 1, regardless of what the value of Y is going to be. The only time you have a false coming out of an implication is when X, which is the one on the left-hand side, is true, but Y, which is the one on the right-hand side, is false. That is the only time when an implication itself is false. Okay?
Can you repeat that? Could you repeat that?
That's it. You know that is a tough question for me because I typically I have no cache there's no buffering, no cache so after I say something it's gone. I think I said so I have to reconstruct everything in my head now. It's like I think I said in implication the only time the implication itself is false is when the first part, the X is true, and then the Y is false. In other words, true implies false itself is false. It's not true, correct. Now that is, you can look at the examples here a little bit because it is kind of cool, okay? So I'm going to look at the statement. Semantically, this can be confusing because I can tell that you guys are kind of confused. It's like, oh, hold on a second here. Implies, what is the result of the implication? Why would implication itself has its own result Boolean value, whether it's true or not. So I'm going to give you an example here. This is a statement. Okay. So you can see how I use the word implies as an operator. So the entire left-hand side, which is a blue cat is sick, is X. And then the entire right-hand side, which is tomorrow is doomsday, is Y. Is that okay? Because each one is a variable. Is a blue cat sick? Well, it can be true, yes, this blue cat is sick, or it is false, no blue cat is sick today. Right? And then the other statement, which is tomorrow is doomsday, is also just a condition. It can be true, tomorrow turns out to be doomsday, or it is false, tomorrow is just another day. Okay, this is kind of funny because I came up with this example before I read a news article on blue dogs in India. You can look it up in Google, but don't do it in class. Because if you like to do it, I can do it here on the projector. But the bottom line was there's pollutants coming out of the factory, and they dump it into the river, and it turns out to dye like light-colored dogs blue. So a whole bunch of dogs bathe or swim in the river with all that toxic dye stuff in the river. So when they came back out, they all turned blue. Well, good thing cats usually don't swim, so otherwise we'll have
Happens.
no. But it can illustrate this particular statement. Now, when you look at this entire statement, a blue cat is sick implies tomorrow is doomsday. It has its own true-false value. Is that okay so far? The implication itself can be true or false. Now, if you're having problem understanding why the implication has a true or false value, it is because most of the time when we use the word implies, we are assuming the implication is true. We never think about, oh, the implication itself can be false. It is just another condition, okay? So I'm gonna do it this way, just so that it emphasizes that the implication itself can be false. So let's say, I'm running a pearls of wisdom service. So you pay me, I will tell you something, right? So as a class, I think this class technically has about 40 students or so. So each one of you will pony up $25, and then as a class you pay me $1,000 for a pearl of wisdom, and that's what I said. That's what I say after collecting $1,000. I'm gonna pass the roll sheet. Make sure you initial your name next to put your initial next to the name. Okay, so after receiving $1,000 from this class, I said, I'll give you a pearl of wisdom. A blue cat is sick implies tomorrow is doomsday. That's all I said. You guys go like, for $1,000? Really? Go like, yep, but you can have your refund if you can prove me wrong. Okay? So now, you guys are all thinking, when can I prove that that statement, the implication itself, is false, right? Because you want your $1,000 back, because you said it's not worth $1,000 or $25 per person. So you're now bent on saying, okay, Tech, I need to show this statement or the implication itself is false, because until you prove it's false, I get to keep your $1,000. Is that okay? All right. Okay. So there are 4 scenarios, okay? The 4 scenarios are spelled out here. A blue cat is sick, and tomorrow is in fact doomsday. In other words, both of those conditions are true. Can you get your money back? No. Well, it wouldn't matter anyway because tomorrow is doomsday. What are you going to do with that $25? But you cannot get your money back. Now, the interesting part are these two. The two in the middle are the interesting ones. What if there's no single blue cat that is sick? the first condition is false, and turns out tomorrow is not doomsday, can you get your money back? Nope. But that's kind of intuitive, because the implication did say something about tomorrow is doomsday, but if tomorrow is not doomsday, obviously the statement is not proven wrong. But the next one is the one that is kind of interesting. No blue cat is sick, and yet tomorrow is doomsday. Can you get your money back? You cannot, because I never said anything about what would happen when no blue cat is sick. And that's why it converts to not x or y. It converts to not, in parentheses, in quotes, a blue cat is sick, or tomorrow is doomsday. Because if the first part is not true, then the whole thing is true. If the first part is false, okay? If the first part is false, then the implication is by default true. You cannot get your money back. Is that okay? So the only time you can get your money back is for the first part to be true. Somebody brings a blue cat to class that is sick, and tomorrow is not doomsday. Then you can get your money back. Yep.
Wouldn't it be neutral, like if x is false, like then it's not really implying anything, it's not testing anything in that case?
But the statement itself still needs to, you still have to say whether it's true or not. Because in the example, I still have to decide whether to refund you or not. Not refunding you means the statement is still true. So are we doing okay so far with this, or is the example making it even more confusing? Yep.
The only thing I was getting a little confused with how you have the negate x on the example above, where you say first you say that x implies y, and then so I was thinking that we were supposed to negate the x each time. Like in the examples, like blue cat is sick, I was thinking, is it do you actually mean when a cat is not sick, or I don't know? I was getting a little confused with that. Like the
this part is not, yeah.
Where it's the negate x and.
Okay, I see what you're talking about.
If x is false, then it will always be true.
So x implies y is the same thing as not x, I'm using the exclamation point here, or y. That is the definition. Okay, so what we're doing here is we're plugging in the various x and y. So if you look at x, y here, if x is false, y is false, what is not x or y?
True.
Can it be true? If x is false, y is true. If x is false, y is true, the implication is still true.
So if there's no blue cats, you can never show that the aura is wrong.
If there are no sick blue cats, then you can not prove the implication to be wrong, and it is by default true.
It's by default true.
Yeah.
It's only false.
Hmm?
It's only false if the first part of the implication is true and the second part is false.
Yes.
Yeah.
That is the only time that an implication is false. But the key concept here is the implication itself has a value. You can say, my pearl of wisdom is bullshit, and you want your money back. Okay? Yep.
So is implied the same as if?
Well, that's a very good question. Okay, so let me finish this truth table first, and then I'll answer your question, because that is a can of worm. And I like that can of worm because it can upset some other professors. Okay, so let's take this. Okay, well, I'm putting a bar here, just so that to separate the discussion here. What I'm doing down below is not based on, it has nothing to do with the definition of implication, but it is how we use the word. Okay, so x implies y we have several ways of saying this. You can say this as x, if x then y, right? Okay, that's a pretty usual way of doing that. Okay. Which also prompts you to say, oh, what about the conditional statements that you have in various programming languages, right? So you can say if x is less than y, and then, okay, I'm using C syntax here because you should have a C class, at least one C or C++ class before this. I don't know. We'll just say that Z gets 20. Okay, doesn't really matter what I do. Okay, so this is a conditional statement that has no else part, right? If by itself implies just implies. If is implies. So when you look at this statement, you ask yourself, if X is in fact less than Y, we are definitely going to do the assignment statement. Okay, because that's what implication says. What if X is not less than Y? Does it say anything about what to do when X is not less than Y? If you use the definition of implication, it doesn't tell you what to do when the condition is false.
So it does not. So
it is the wrong word to use.
oh.
Because if you want to say if X is only do Z equals to 20 when X is less than Y, you should have said if and only if, IFF. So the phrase if and only if X is less than Y, go ahead and change Z to 20 is logically different from the statement of if X is less than Y, change Z to 20. Because without using if and only if, you are not really saying anything about, oh, what if X is less than Y is false? I don't know. I mean, go change Z or not change Z, it's not specified. So this is a misnomer. In other words, they chose the wrong word for conditional statements. They should have used if and only if, so that we know what to do when the condition is false. When the condition is false, don't do anything with Z in this case. So is that answering that question earlier about? Nope. Okay. All right, so that's implication, and this is equivalence. Equivalence is actually pretty easy. You can look at equivalence as two implications. So when you say X is equivalent to Y, then you're basically saying X implies Y and Y implies X. So in this case, they are tied. When one is true, the other one has to be true. When one is false, the other one has to be false if the equivalence itself is true. Are we doing okay so far with this stuff here? Oh, thank you. Any questions? Yep, go ahead.
My question is that because implication is easier to implement in computer, so that's why we wanted to convert the equivalent to?
Well, implication is a very important operator because whenever you do a proof, you are using implication. Okay? Every single proof that you do in any mathematical class is making use of implications. Now, it may be implicit, but you are using implications.
So it's for the sake of proving the concept is true.
Yes. So when you're proving a theorem, which is a proposed statement, and you say, I'm suspecting this statement is true, so how do you make sure it is true? You have to use implications. I will draw this picture at least once now. You can copy it now. You can copy it later on in the semester. Because we will get back to this later on. When you look at axioms, okay. So let's say these dots here are all representing axioms. It doesn't even matter which field of math you're dealing with. This is just in general. Okay. We have a whole bunch of axioms, and then this is the theorem. This is representing the theorem that you need to prove. Okay? So a theorem is basically a proposed statement that you suspect is true. When you combine these axioms, okay, you can say that these two together implies this one here. These two combined may imply this. These three combined may imply this. Okay? These two combined may imply this. These two combined is implying the theorem. Huh? Yeah, I know it's kind of faint. But you get the idea. Let me see if I can find a different dry board marker. They don't have one. But the idea is You start off with axioms where they are given to be true. They're assumed true. You don't question the truthfulness of axioms, right? So you combine the axioms to have their own implication, their own results. Other ones will combine to other results, and then you look at these results and they go like, oh, we can combine those two. So they would, but every single step along the way, you are using implication. In other words, when you prove a theorem, you are basically creating a chain, okay, or a mesh of implications that starts off with the axioms, but ending with the theorem that you're trying to prove. And that's why implication is of great importance in any type of math class. Now, most of us use this implicitly in math classes, but in this class, you will see that we're going to use it much more explicitly. Are we doing okay so far or not? All right, so we are done with Boolean operators as a module. And we are now moving on to the next one, which is basic set theory. I think some people might have exposure to set theories, in high school, and some people may not. So let me just do a quick survey. Who has exposure to set theory in high school? Okay, a few. Okay, so the majority did not. Okay, that's fine. Not a problem. I just need to know the proportions. Okay, so let's go ahead and talk about what a set is and what is an element in a set. A set, yeah, go ahead, question? No? Oh, okay. A set is a containment of elements, okay? In other words, a set can contain elements. It's just, these are just terms, okay? So at this point, we're just looking at the terms here. The most basic concept of a set theory is the concept of a set containing or not containing a particular element. In other words, membership is what we are talking about here. Okay, so if you really need to remember what a set is in much more practical terms and what an element is in much more practical terms, you can just think about a set as clubs, student clubs. Okay, since you're on campus, let's talk about student clubs. So a set is basically a student club. It's a container, and then you have individual students kind of floating around. And then you can ask the question, is this student a member of this club? That's membership. So some really popular clubs may have 200 elements or more as members. And then the computer science club only has 3. And those are all the officers of the club. Okay? So are we doing okay so far with that analogy? A club is like a set, and you can establish whether something is a member or is not a member of that set. Yep.
So can elements be members of different sets?
Oh yeah, absolutely. Just like a student can belong to many different clubs. Yep. In fact, that is really important when we talk about how a set can relate to another set, whether there's an intersection, that sort of thing. All right, so we do okay so far with the containment or membership concept. A set is a container, and then membership establishes whether things can be in that particular set or not. Now, ordering is not important in a set. In other words, when I represent a set and say that, oh, this set here has element A, B, and C, and the other set has elements B, C, and A, they are the same set, okay? Because ordering is not important when you are looking at membership inside a set. So that makes it different from an array, because you guys know about arrays from all your other classes. In an array, ordering matters, okay? If you have an array with the values of 1, 2, and 3 as elements, and you have another array with the elements 3, 2, and 1, did I say 3, 2, and 1 the first time? I said 1, 2, 3? Okay. So these two arrays are considered different. Okay? But in a set, in the case of a set, how you spell out the elements doesn't really matter. Because the true representation of a set doesn't have ordering in it. Is that part okay? Because that part does not map to anything that you deal with in programming. And the last important part, concept of a set, is that elements in a set must be unique. In other words, when you look at elements or when you list elements inside a set, you cannot list the same thing twice. Is that okay? But with an array, you can easily have an array with 4 elements and they are all having the same values. Not in a set. Okay? In a set, if you say that there are 4 members in a set, those 4 members must be different values, or they must be different from each other. Is that okay?
So you can't have like 1 and 1, you just have to have 1 in a set.
That is correct.
Okay.
Or if you look at it differently, if you tell me that this set has 2 elements, and you know one of the elements is 1, then I know exactly that the other element cannot be a 1.
Okay.
It can be anything but 1.
All right.
Okay. All right. So once we understand the basic concepts, which is a set is a club and you can have membership, we can now start to introduce symbols. Typically, we use an uppercase alphabet letter to represent a set. Okay, it's just convention. It's observed by most publications, and then we use curly braces as the delimiters of the containment or the content of the set. So in this case, these 2 curly braces or just braces represent okay, where does it start and where does it end. And then we just have a comma-separated list of items inside the set. And you can see how these things are not exactly sorted because the ordering does not matter. Okay, if I want to move the 10 all the way to the first element, okay, that's good too. But you also notice that we do not have duplicate values because a set can only contain unique values. There cannot be duplicates. Are there questions about this notation, how we represent a set T contains the elements of 12, 5, 2.2, 7, -1, and 10? No questions? Okay. And if there are no questions, the next symbol, which is kind of related to this one, is to show whether something is an element of a particular set. Now, when you look at this, it is not an assertion. In other words, it's not telling you that 2.2 is in fact in the set T. It is a question of whether 2.2 is an element of T. It can give you a result of true, yes, it is in the set, or it can give you a result of false, where 2.2 is not an element of T. Okay, so it is very important to look at these operators and make sure that we know that they are not saying it is an assertion, instead it is a question. Okay. Section 3 talks about how we establish equivalences of sets. In other words, if we look at one set, we look at another set, can we say that these 2 are the same? Okay. So a set can be compared to another set to see if they are the same. At this point, we lack the precise mathematical notation for this kind of discussion, but we can utilize English for the most part. Let's say we're interested in whether set S and set T are the same. These 2 are considered the same when every element in one set is in the other set, and every element in the other set is in the first set. Yep, it has to go in both directions. If this requirement is satisfied, then we can say that these 2 are the same. Yep.
You said like E could only be used as a question. Could it also be used as an assertion in other cases?
When you, if you say it's an assertion, then you can say given that, blah, 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 blah. So when you say given that, then you are saying, okay, I'm asserting this, or at least I'm assuming that. Yep.
And sets are not restricted to a particular type.
No, they're not. There's no type restriction. So unlike C and C++ programming, where it's a strongly typed language, when we use mathematical symbols, there's no inherent type limitation. So you can have a set that has names and numbers and cars and elements of chemistry elements and whatnot, kind of mixed up in the same set. That's okay, not a problem. Yep.
Can you have sets of sets?
Yes.
Our set, an array of arrays.
And that's section 4. Very good. So you're so that means I'm ordering these topics correctly. It's a good feeling that when you guys ask a question and it's the next one, because it's just naturally leading to the next question. Okay. So a set can be an element of another set. There's no limitation saying that you cannot do that. Now, to understand this part, because it seems to be confusing, you can kind of think about these as a set as a folder. Can a folder be a part of another folder?
Yeah.
Yep. Okay, well, there you go. Okay.
I've heard that statement, the set of all sets that does not contain the set itself. Who was the mathematician that said that one? I forgot that one.
Okay, cannot contain itself because that would then it
like,
would be recursive.
Yeah, it's like a self-contradictory statement.
Yeah. Yep. I don't remember, but you can probably Google search and
Yeah.
find it.
What's
Okay.
the set of all sets have to contain itself?
It doesn't contain itself in the definition.
So if you're given two things, lowercase x and lowercase y, knowing that x is a set already, asserting that x is a set, how do we determine that x and y are the same? The first requirement is y has to be a set. Because if x is a set but y is not a set, then x equals y has to be false. Because you're comparing a folder to a file. They're different things, right? They cannot be the same. On the other hand, if you know that y is also a set, then we use the set comparison method that we talked about here in section 3 to establish whether x equals y is true or not. The question mark is supposed to resolve to section 3, but for some reason it's not doing it. I will try to fix that. Yep.
So we just use the equal sign if two sets are the same?
Yes.
Okay.
Mm-hmm. So now we can compare a set with anything for equality. And it is not surprising that you can have one set being an element of another set. So if you know that x, as a set, uppercase X is a set, it has, how many elements do you think X has?
3.
It has got 3 elements. Very good. Because it has got the first element, well, I shouldn't say the first because ordering is not important, but one element is A, one element is B, and then the one element is a set itself containing its own elements of 1, 2, 3. Okay, it's just like a folder. Remember folders? You can have a folder containing a file, and then another folder. And then the subfolder itself contains 3 files on its own. Same concept.
Just out of curiosity, does the set contain itself?
A set cannot contain itself, which is what he talked about just a little bit earlier. Yeah. Yep, go ahead.
Since we note sets with just uppercase letters, if we had wanted, instead of putting A, B, and then writing out the inner set, if we had just wanted to put X in there, is there some special notation we could use to designate that X is a set and not just the uppercase letter X?
No, we don't have any particular way to assert that X is a set other than just spelling it out and say that X is or is not a set. Okay, question?
Can an improper set contain itself?
And an infinite set. These are finite sets.
Ah, very good. See, section 5 talks about sets with an infinite number of elements. But it cannot contain itself. A set cannot contain itself. Because otherwise it becomes there's an issue. Because you never know what is an element of that particular set.
You can't say like 1 is an element of X because it's not a set of 1, 2, and 3, right? For that to.
That is correct. 1 is an element of X is false.
Okay.
The set 1, 2, 3.
Hmm? Yeah, the set 1, 2, 3 is an element of X is true. But what you said is also true. 1 by itself is not an element of uppercase X.
Okay.
Yep.
Is there a not for the epsilon?
Yeah, there's a you can put a bar across the epsilon to say that something is not an element. But I tend just to say not blah 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 is an element of, just so that that works better for me because it's more orthogonal. There's only one way to express it. But yes, mathematical symbol wise, there is a element of with a bar. All right. Do we have any questions at this point? Yes.
So just a second ago, we were talking about that one is not a member of X. That it's all if you have a set within a set, you always consider that whole set a member, not the individual components.
Well, okay.
Or
So let's use an
those
example.
little
That's a
details.
very good question. So we'll use another example here. We'll use Z here. So Z is a set with 1 as an element, the set of 1 as an element, the set of 1 as yet another element. It's okay. It's perfectly okay to have a set that looks like this. Because Z is a folder, right? It's a folder that has 3 items. One item is a file by itself. One item is a subfolder with a file. And then another item, the third item, is a folder with a subfolder with a file. And those 3 files, quote-unquote files, turn out to be identical. But that's fine. Yep.
So it's fine to have a set containing only one element?
You can have a set containing one element, you can have a set containing no elements. So we'll talk about the empty set a little bit later. Yep, go ahead.
So within this one, with the Z example, even though they're identical, is each element different? Though?
Yes, they are considered different.
Okay.
So they are unique elements. Yep.
So being a set is basically a property, and if there's like a set of a set, then there's more properties to that element, basically.
A set is a container. Look at it as a folder as opposed to a file. So anything that is not a set is a file, but a folder is basically equivalent to a set. It's a containment for something else. Yep.
So if 1 wasn't in Z, the first element, then technically 1 by itself wouldn't be in the set. It would have to have reasonable for it to be its own set.
Say that one more time.
So if you take out the first element, then 1 wouldn't be in set of Z.
That is correct. Now let's change this a little bit so this makes the discussion easier. Okay. So in this case, 1 in Z, instead of using the epsilon symbol, when I spell it out, I just use in to say whether it's a member of. So 1 in Z is true, right? 2 in Z is false. But the set with 2 in Z is true. Is that okay? And you can probably tell 3 in Z is false. The set of 3 in Z is also false, but the set of 3 in Z is true. Is that okay?
So it's the set, so Z contains 1, and the set of 2 in the set of Z is true, and the set of 3, and the set of 3 within the set of Z is true.
Yes. Yep, that's correct. Yep.
Can you specify, like, 3 is in a set of a set in Z? Can
3.
you specify, can you like do jumps? Like say there's 2 set, there's a,
Right.
there's a, yeah.
I don't think there's any quick shortcut to do it.
Yeah.
None that I know of. Yep. All right. So, are we ready to move on to talk about there are certain sets that have an infinite number of members?
Just a second.
Okay. I think the best way to look at a set is a folder, because you cannot have 2 folders of the same name. You cannot have 2 files of exactly the same name in the same folder. Yep.
If we have an empty set inside of a set, will we say like it has 1 element?
Yes.
Empty set within a set.
Yep. When we get to empty sets, then we can talk about those kind of interesting cases. You can have a set with an empty set, but the outer set is not an empty set itself because it contains an empty set.
So the empty set inside is considered an element.
Yes.
Nothing.
Wow. Okay.
Yep. But it still maps to the folder concept. Because if you have a folder that has a subfolder, but the subfolder has nothing in it, you can call the subfolder itself empty, but you cannot call the top level folder empty because it has got one thing in it. Yep. Yeah, too bad, back in those good old days, mathematicians did not have computers with folders, right?
Now we're so used to it.
Yeah, otherwise it would be easier to explain those concepts.
It's just file cabinets. It's the same sort of idea, right? File cabinets.
But it's harder to have a file cabinet with a file cabinet inside. you can kind of conceptually visualize that.
Like folders.
That'd be
in a
cool.
file cabinet.
Yeah, you can have folders, and then you can have dividers first, and then folders,
Yeah.
drawers first, right?
Yeah.
File cabinet, and then you have drawers, and then within a drawer you got these folders.
It goes in the buildings, cities.
And then people will say, oh, but you can only have like 6 levels of containment because physically it's not possible to have any more. Okay, so if you want to represent all the even numbers, okay, so if you want to display or specify a set of all the even numbers, all the even integers, how do you do it? Well, you can spell it out, right? You can just say, set E is the set of all the even numbers. Okay, that's kind of cool. Okay, that works. You can kind of give people an example of what's in it so that people can generalize and just say that, oh, okay, so I'm assuming the dot would be -6, -8, -10 on one side, 6, 8, 10, 12 on the other side. But that's not very precise, okay? Because you might end at a certain number, and stop the range. It may not be infinite. So we now have a notation, which is down here, so that we can specify, it's a different way of specifying membership inside a particular set. So this is basically saying, X is an element of this particular set if and only if X is also an element of Z, which represents the set of all the integers, and X mod 2 has a result of 0. Sorry? Oh, okay, okay.
Means it's an means it's an even number.
Yeah. Okay, so let's take a look at this one here. Okay, so the first X here is basically just saying, okay, I'm using this as a symbol of a particular element in this set. Okay, so this lowercase x is just a placeholder so that I can refer to an element in the set E. The bar can be read as such that. You can also look at it as if and only if. In other words, you're basically saying X can be an element of E if and only if the following is true. Are we doing okay so far? Now, note that I used if and only if, not just if. Okay, if and only if is very important in this case. The rest is basically specifying a condition that must be met in order for something to be an element of E, and anything that meets this requirement has to be a member of E as well. That's where the if and only if comes in, because it's not just saying, oh, everything in E has this, satisfies this condition. That's a part of it. But the other part is saying anything that meets this requirement has got to be a member in E. So that's the bidirectional thing, which you get from if and only if. Okay. So now that we look at this part here, let's look at the first one. X is an element of the funky Z character. That means X is an element of the set of all integers. It is by mathematical convention that this particular symbol, the funky looking Z, represents the set of all integers. I think it's explained somewhere else later. But you also have a second condition. Oh, I think I have an extra bar here. So forget about this bar.
Oh,
huh?
Yeah.
Yeah, I got an extra bar.
It kind of reads like it makes sense, but I guess it's extra.
Should a comma be there instead?
No, this is a conjunction, so this bar should just go away.
Oh, okay.
Let me fix that. It's pretty easy to do it.
Yeah, when I was reading that before class, I was a little confused.
Sorry about that. And this is 280, I think. Then Okay, I'm just looking for the words here that I can use for searching. So bar, open paren, okay. Bar, open paren. There we go. Yep, that's the extra bar here. So this is how I type my class notes. It's in the native form of LaTeX, and all I need is just a regular text editor. I kind of spoil myself using Vim because it has got syntax highlighting, but Notepad would work just fine. It's just that I won't be able to catch some of the stuff, quickly. So that's basically it, and then I save the file, and then I run a tiny little script called publish. It will run through the LaTeX engine to render that document in both HTML and PDF, and it will also automatically upload it. Well, the script does that. It will upload it to the server. So now when I go back to the server and refresh, it should have that bar removed. Maybe not that one. Oh, this is the wrong place. Oh, okay, never mind. Okay, I'm on the wrong server. I'm on the wrong server here. This really should be. Well, it is Moodle. Moodle, is going away, and that's why I have a new server to do this. arccis.net. There we go. Too many servers to maintain. There we go. Okay, now it's fixed. So you can probably imagine how what is the process of typing all these notes. It's not what you see is what you get. Is that okay so far? Okay. All right, so with that bar gone, this is correct now. So we have two conditions that must be true in order for something to be a member of E. First one is it has to be an integer, and number two is the remainder of that number divided by 2 has to be a 0. That's a really long way of saying it's a multiple of 2 or it's even, exactly. Okay, so this condition, the one that is being highlighted right now, says that x is even. Yep?
If you change the 0 to a 1, it would be odds, right?
That is correct. Or you can just put a bar across the equal. If it's not 0, then it is odd. Yep.
That's the x mod 2 that makes it even, you said, right? You said it makes it even, the x mod 2 equals 0?
If x mod 2 equals 0, it makes it even.
Yeah.
Yep.
Do you even need the x as part of all integers then?
Say again?
Do you even really need the condition of x as part of all integers? Because if it was a real number, like a decimal divided by 2, it still wouldn't equal 0.
True, but complex numbers can, because complex numbers can also be divided, but it depends on how you define 0. Yep.
So this reads within a set of E with an element of x and x being an integer that can be divided by 2 with a remainder of 0 is true.
Okay, so if you want to read this out, just not using mathematical symbols, it is saying E is a set as follows. Okay, and then on a separate sentence, you say, in this particular set, for anything that, and x is an element of E, if and only if x is an integer, and the result of x mod 2 is 0. Is that okay?
Yeah.
Yep. So it's really, but it's a lot more concise when you look at it using the mathematical, symbolic way. But when you read it out, then that would be what I just said. E is a set where x is an element of that set if and only if x is an integer and x mod 2 is 0.
Sorry, is there
Yep.
a symbol in there that represents if and only? What symbol in there represents if and only?
The bar.
Oh, you can also, the implies, you can do the two-sided implies, where it's the 2 arrows, one arrow pointing one way and one pointing the other.
Yes, but not inside the curly brace, because the element of thing is not used inside the. Okay, so But that's a very good question. I'm so glad that you guys asked the question. Okay, so in this part here, I'm using P of X as a general quote-unquote predicate. In other words, if you look at this from the perspective of functions in C and C++, P is just some function that returns true or false based on X. It has a parameter X. It is returning 0 for false and non-zero as true. Is that okay? Okay, so it's just a criterion that is either true or false. So the notation that I used here is really a shorthand of this notation here. They mean exactly the same thing. Okay, so let's take a look at what this one is saying. This one says X is an element of E if and only if P of X is true. Okay. The other one is saying E is a set where for each element of the set, P of X has to be true. And anything that makes P of X true has to be an element of the set. Yep.
Is there a specific notation name? Because are you going to have like on the test saying, oh, put it in this notation, or convert it from this notation?
No. Yeah, well, there's usually no conversion, questions, or no, there will be no memorization questions. So I'm assuming that you know how to read these symbols. So the questions are mostly problem-solving questions. Okay. So is that okay? Because this is exactly what you guys were trying to figure out, or somebody was suggesting, is can we re-express this using the equivalent, if and only if symbol? And yes, you can. But when you use the if and only if symbol, then you're not using the set notation anymore. Instead, you have to use the element of symbol to mean exactly the same thing. Is that part okay? Or any questions about this so far? Yep.
Speaking about exams, do you have any sample exams so we can see what the format looks like?
Yeah, I do.
Do you post those on?
Well, since I maintain all my lectures, all the previous lectures, so they're already in YouTube somewhere. It's just a little bit hard to fish and find it.
Yeah.
Because I review all of the exams. So 1 week before the actual exam, I'll give you a practice exam. The practice exam is the actual exam of the semester prior. And then after the exam, I will go over the questions of that particular actual exam. And all of that is recorded on YouTube. Yep.
So this within the set of E, the element X is if and only if when it's put into the function.
If and only if when you apply the function of P, it gives you a true as a result. And
yeah, I'm a little confused because if you have X as an element of E, does that really map to a set, or does it just map to one of the elements of the set? Or is it saying that X can be any element of the set?
This is a statement that is always true. I'm asserting that this statement is always true. So you pick some X out of the entire universe. Okay, pick something. Pick my car. Okay, out of the entire universe, and you say, well, this is always true. So we can evaluate this one, right? This one is saying, okay, is X an element of integers? No, my car is not an integer. So this part is false, right?
Okay.
But because we know the equivalence is true, when one side is false, we know the other side is false as well. So now we know my car is not in the set E.
Okay.
Okay. Yep. Go ahead.
If you have multiple variables like X and Y, are they going to be in the same set?
There will be cases later on where you can have multiple variables, because each element in the set involves multiple parts, but not right now. Yes, go ahead.
The online doesn't have that part. Your online, your website on Canvas, and that section is missing from the
Yeah, I think I got the wrong link in Canvas because I did some of this before I converted to the other server. And that's why, but that's good. Thank you for pointing that out. Let me change that right now because it linked to the wrong server. So all I have to do is to change this one to arccis.net. Update. So now it should be updated. But thank you for pointing that out. Any other questions about the set theory or just the notation? Right now we are mostly just talking about notations. It's like learning a new language, but it's easier. Okay, to me it is easier. Okay, if I were to learn Spanish, it would take me a decade to even be useful in conversation. This stuff, I can learn this stuff fairly quickly. Yep.
Could you explain I forget already, the thing you have highlighted? You
Okay.
said X.
Yeah, this one is, if you read it out, it's basically saying this is a set where each element X has to meet this requirement. But
What is
the requirement is P of X has to be true. P is some kind of Boolean function that you can define. You can say, oh, it has to be this, has to be that, can have conjunction, disjunction, and whatnot. But P of X, P has to return either true or false based on X. So this is saying, X is an element of this particular set, but in order to qualify that membership, this has to be true.
So you could replace X with a 1 or something to I don't know.
No, X has to be a variable.
X is a variable. When you put it into the function, if it returns a 1,
it has to return a 1 if it is a member.
If it is a member. So if that's a Y or something.
Or you can say every member X in this set satisfies this requirement.
Oh, that's just a defining statement. Okay.
Yep. It's just it's a notation to define what is in that particular set.
Yeah.
All right. So this is the end of the class. If you're trying to add to the class, come forward and pick out a add number, but we have to do it quickly because I have to move on to the next class, which is not here.
Will it be the PDS for the next lecture up over the weekend?
Yeah.
Okay.
Yeah, just remind me if you don't see it.
Okay.
Just go ahead and remind me because I have it already authored. I just haven't linked it.
Okay, I'll wait till like Saturday.